This is a lab called Visualizing the Mole. As we begin to work with reactions and the quantities of different chemical substances, it's really important to get a tangible grasp of the concept of a mole. So in this lab, we're going to walk through several stations, 6 of them in fact, where we're going to be asked to either calculate or measure the amount of 1 mole of a substance. In station 1, they're going to ask us to pour out 1 mole of water into a graduated cylinder. Remember that for water, 1 milliliter equals 1 gram. That's its density as defined by the metric scale itself. Now, H2O is water's formula, so the mass of 1 mole of water can be found by adding together the atomic weight of 1 atom of oxygen, which is 16, plus 2 times the atomic weight of hydrogen, each of which are 1. So 16 plus 1 is 18 atomic mass units. Now, Avogadro, the Italian scientist, discovered that, hey, if we've got a certain number of atoms, then that atomic weight in AMUs, or atomic mass units, is equal to its mass in grams. And as it turns out, that same number of atoms would apply regardless of the substance that we're dealing with. So let's start with water. If 1 gram is equal to 1 milliliter, and I have a grad cylinder here, if I pour out 18 milliliters of water, I should have 1 mole of water. There we go. So I've poured out 18 milliliters of water. Just to give you a visual of that, if I were to pour this into a small beaker, it doesn't even halfway fill the beaker. You could easily take a sip of this, and I'm not going to do that right now, but the lab does invite you, if you so wish, to take a sip of some clean water that you would easily be able to swig. Now, it's hard to imagine just how small an atom is. 602 hexillion atoms or molecules of water are in this small of a size sample. The beautiful thing about the mole concept is that we can use such a huge number to let us translate something that's really, really small, like atoms and molecules, into something that's workable on a lab scale. I can work with this amount of water, but if you get much, much smaller than that, I'm going to either need specialized equipment or I won't be able to do this. I might be able to do something on micro scale, but it gets really hard to work with small amounts of substances. So station 1 is complete. Oh, here are some fun questions. If a cube were filled with pure methane gas, what would be the mass of this gas? Well, methane is CH4, and its molar mass could be found by adding together a carbon, which is 12, plus 4 atoms of hydrogen, each of which is 1. So 12 plus 1 plus 1 plus 1, that would be 16. And if they're saying if you've extracted a mole of CH4, then you would have 16 grams of CH4. Same thing as that for water. If water's molar mass is 18, then 18 grams of water is 1 mole. So each of the stations in this lab are going to end with a question, and the answer should always be the same. How many molecules would be present in this sample of the gas? Well, if it's 1 mole, guess what, students? It's going to be Avogadro's number of molecules. 6.02 times 10 to the 23rd. Even up above, it says how many molecules of water are in our sample here. 6.02 times 10 to the 23rd. Station 2. In station 2, we're going to use 2 samples of metals. They're both samples that are 1 mole each. One of them is zinc and one of them is tin, and they're both somewhat shiny, grayish colored metals. But at first, I wouldn't know which one is which. What I'm going to use to figure out which one is which is the mass. So I'm going to use my electronic scale. I'll turn it on. And we're going to record, or at least note, the masses. So sample A is one of the two metals. And when I set it on the scale, I'm getting a reading of 124.11 grams. Now, the bag itself, the plastic bag, weighs 5 grams. So I'm going to subtract 5 from that, and I get 119 roughly, okay, grams. Now, let's look on the periodic table. Zinc is element number 30, and its atomic weight is about 65. Tin is element number 50, and its atomic weight is about 119. Hey, this is tin because I know I've got a 1 mole sample. Let's verify that by weighing the other bag. Here's the other grayish metal in a plastic bag. I'm going to set it on the scale, and I get a reading of 69-ish, 68.9. So let's call it 68.9. If I subtract the mass of the bag itself, which is 5 grams, from 68.9, I get 63.9. Well, students, zinc has an atomic weight that's pretty close to 63.9. It's 65.38. Within normal amounts of error that you could encounter in lab, we can confidently say that this is zinc, sample B is zinc, and sample A is tin. Okay. Station 2 asks you at the end, how many atoms of zinc are there in the 1 mole sample? That would be, again, Avogadro's number, 6.02 times 10 to the 23rd. On to station 3. Again, we're going to use samples that are 1 mole each. This time we're dealing with white powders. Sample A and sample B. We don't know which is which, but one of them is calcium hydroxide and one of them is calcium carbonate. Ooh, okay. Now, we have to figure out which one is which. And the way to do that is to think about their molar masses. Let's first weigh the two samples. And I'm going to show you some work on the board to clarify station 3. But for right now, let's record the masses. Sample A has a mass of 105.4 grams, 105.4. And if I subtract out the mass of the bag itself, which is 5 grams, that leaves us with 100.4 for sample A. Sample B get 80.5, 80.5. And again, let's subtract out the mass of the bag itself, which is 5 grams. And that would give us 75.5 grams. Okay, now let's do a little board work. Students, now we need to do a little bit of board work for station 3 in order to figure out which sample is calcium hydroxide and which one is calcium carbonate. To figure this out, we're going to do a standard molar mass calculation. Let's start with calcium hydroxide. The way I typically like to do this is I write the compound's formula and I underline it. Below that underline, I'm listing all of the elements that we see. So whenever you see a capital letter, that's a new element. So I see calcium, I see oxygen, and I see hydrogen. Based on the formula and the implied subscript of 1 for calcium, I'm going to write down 1 atom of calcium times the atomic weight that we'll look up in just a minute. I see, because of this subscript 2 that applies to both the oxygen and the hydrogen, we've got 2 atoms of each of oxygen and hydrogen. Now, we pull out our periodic table, and we're going to look up and find calcium, column 2, and I usually round those atomic weights to the 10th place because that offers plenty of accuracy without having to go overboard with the number of significant figures. So 1 atom times 40.1 gives us a result of 40.1. Oxygen, column 16. If you round the atomic weight to the 10th place, we get 16.0. 2 times 16.0 gives us 32. Hydrogen, up in the upper left corner. Rounded to the 10th place has an atomic weight of 1.0. 2 times 1.0 gives us 2.0. Now we're going to add the results together. 40.1 plus 32 plus 2. And we get 74.1 grams per mole. So that means for every 74.1 grams of calcium hydroxide, you'll have 1 mole of it. We'll be able to use that info to figure out which sample is the calcium hydroxide and which one's calcium carbonate. Now, for completeness sake, let's also talk about calcium carbonate, the other solid white powder that we encounter in station 3. Again, we're going to write the compound's formula and the elements that are present. Looking carefully at the subscripts within the formula. If it's an implied 1 subscript, we'll write down 1 atom. We see that both for calcium and carbon. And we see a listed subscript of 3 for the oxygen. Now we refer to the periodic table. Again, calcium, if you figured it out over here, you figured it out forever. It's 40.1. But if you did ever want to look it up, you could always find calcium in column 2 on your periodic table. Carbon, column 14, it rounds to 12.0 if we give it to the 10th place. And then oxygen, again, we saw that in the previous compound. It was 16.0. And 3 times 16 equals 48. Okay, let's add these up. So 40.1 plus 12 plus 48, that's 100.1 grams per mole. So for every 100 or so grams of calcium carbonate, you've got 1 mole of it. And that'll enable us to identify which one's which in station 3. Okay, so now that we've established the molar masses for both calcium carbonate and calcium hydroxide, which sample, the one that weighed 100.4 grams or the sample that weighed 75.5 grams, do you think the calcium carbonate was? Well, of course, calcium carbonate's calculated atomic weight or molar mass from our board work is 100.1. That's very close to the measured mass of 100.4. So sample A is calcium carbonate. The other one, calcium hydroxide, we measured its mass to be 75.5 grams, and its calculated molar mass is 74.1. Again, very close. So sample B is calcium hydroxide. On to station 4. Take a look at these. First of all, the size of these 2 samples. This one is especially large. Sample A is a bag of a 1 mole sample of either salt, sodium chloride, or sugar, sucrose, C12H22O11. Sample B, again, is a 1 mole sample of the other thing. Whatever A is not, B is. So again, let's first weigh these samples. We'll note their weights, and then we'll do a little board work and come to a conclusion. So sample A, I'm going to carefully set it on the scale here. I get 329.5 grams. 329.5 for sample A. Sample B, if I set this one on the scale, I'm getting 57.6 grams for B. Okay. Now we'll pause and do some board work to confirm their molar masses. Station 4 is another one of those where we need to do a little work to figure out which compound is which. They gave us 2 white solid powders, sodium chloride and sucrose or sugar. Let's calculate their molar masses. So NaCl is sodium chloride, and in that formula, there are 2 elements, Na and Cl. They both have subscripts of 1 in the formula. So I'm going to write down 1 times. And then for sodium's atomic weight, I'm looking in column 1. And if I round it to the 10th place, I get 23.0. For chlorine, I'm looking in column 17 and round that atomic weight to the 10th place. Add the two results together, and we get 58.5 grams per mole. The other white powder is significantly larger. If you look at the formula here, C12H22O11, there's a lot of atoms in that formula, and that probably tells you something about the weight. It's going to be much bigger, a much bigger molar mass. Elements present, CH and O. The subscripts within the formula are each 12, 22, and oops, I wrote 12, but I meant to write 11. And these are atoms whose atomic weights we've worked with before, but in case you forget, you can always look them up. Carbon is in column 14. The atomic weight, if you round it to the 10th place, is 12.0. Hydrogen, upper left corner, atomic weight of 1.0 if you round it to the 10th place. We have 22 of those. That rounds to 22, calculates to 22. And oxygen, rounded to the 10th place, is 16. Now that's a number I need to punch into my calculator. So 11 times 16 gives me 176. We'll add those three numbers together, and we get 342. That's a big compound. So 342 grams per mole as compared to a much, much smaller 58.5 grams per mole ought to be able to help us figure out which one's which in station 4. Okay, now that we've calculated the molar masses of both sucrose and sodium chloride, the one that is the bigger sample was 329.5 grams. Now, our calculated molar mass for sucrose, 342, is a little bit off, but students, percentage-wise, that's still well within reasonable laboratory error. So, and it's definitely much, much larger than sample B, whose mass was measured to be 57.6 grams. That one, sample B, is much, much closer to sodium chloride's calculated molar mass of 58.5. Thus, we conclude that sample A is sucrose and sample B is sodium chloride. All right, station 5. Here are two different samples of the same metal. They're not necessarily 1 mole samples. It's the same sample. One of them is a 1 mole sample and one of them is not. First, let's weigh the two samples. Sample A, if I set it on our scale, I get 107.1. And if I subtract the mass of the bag, that would give us 102.1 grams. Sample B is heavier. I can already feel it. If I set this one on the scale, I get 210.4. If I subtract the mass of the bag, that gives us 205.4. Now, this one's going to be a pretty straightforward lookup. If we go to the periodic table and find Pb, that's lead, it says the atomic weight is 207.2. Well, the sample that's much, much closer to 207.2 is sample B, which had a mass of 205.4. Again, that small difference between 205.4 and 207.1 is negligible in a lab setting. But sample A is significantly less. It's about half of a mole. It's down at 102.1. So if we were to answer the question, which sample is not 1 mole? It's sample A. What is the mass of 1 mole of lead? It should be 207.2 grams. I got that number from the periodic table. And how many atoms are in the larger sample? Well, Avogadro's number, 6.02 times 10 to the negative, or 10 to the positive 23rd. Last station, station 6. Again, we have bags of white powder. Here are 2 samples of sodium bicarbonate, NaHCO3, also known as baking soda. Okay, so this is just household baking soda. We're not telling you which one is a mole and which one is not a mole. We're going to figure that out. First, let's get some masses, and then we've got to do a little bit of board work to figure out the molar mass of sodium bicarbonate. So here's sample A. If I set it on the scale, I get 52.4. And if we subtract the weight of the bag itself, that would give us 47.4 grams. The other sample, sample B, I put it on the scale, 84.9. And if we subtract the mass of the bag itself, that gives us 79.9. Okay, so let's do a little board work to find sodium bicarbonate's calculated molar mass from the periodic table, and then we'll come back and draw our conclusion. In station 6, we're working with baking soda or sodium bicarbonate. We just need that one compound's atomic molar mass so that we can compare the 2 different size samples of that same compound. And in doing so, we'll figure out which one is the 1 mole size sample. Within the formula, we see Na, sodium, H, C, and O. So there's 4 different elements here. Looking at subscripts, if it's an implied 1 subscript, we'll just write that down as 1 times something. So I see that for sodium, for hydrogen, and for carbon. The oxygen has a subscript of 3. Now we refer to the periodic table. Sodium, column 1, its atomic weight is 23. You round it to the tenths. Hydrogen, column 1, way up at the top, 1.0. Carbon, column 14, 12.0. And oxygen, column 16, 16.0. And there's 3 of those. So 3 times 16 gives you 48. Now we pull out our calculator, and we're going to add together the numbers in the column. So 23 plus 1 plus 12 plus 48. And we get 84 grams per mole. Knowing that, we'll be able to calculate which of the samples A or B is the 1 mole size sample of sodium bicarbonate. Thanks, students, for your good work. We know that sodium bicarbonate's measured molar mass or calculated molar mass from the periodic table is 84 grams per mole. Of our 2 samples, sample A was much less than that, 47.4 grams. And sample B was much closer, although not exactly the same. I got 79.9 grams. That is, sample B, therefore, is much closer to the actual molar mass of sodium bicarbonate. So we would conclude that sample A is not a 1 mole sample. It's much less than that. The mass of 1 mole of baking soda, 84 grams. And how many molecules are in the larger sample? Or we should say formula units, because it's an ionic compound. It would be Avogadro's number, 6.02 times 10 to the 23rd. Our hope is that with this lab, you've gotten a little bit of a sense of the tangible size of a 1 mole sample. And if atoms are so very, very small, we need to be working with enormous numbers of them in order to provide sizes that our limited instruments like this electronic scale can actually register and work with in lab. Thanks for your good work.